All right, today we're going to be learning about polynomials, their leading coefficients, and then finally end behavior. So we're going to start with what standard form is. So if you look at these polynomials, these two examples, you'll see they're both not in standard form. So first of all, standard form, the polynomial, each term, they need to be separated by either addition or subtraction. Additionally, the degree needs to go in descending order. And then finally, you need to make sure it's simplified. So you can't have any like terms that aren't combined. So in this first example, 7x squared plus 6x to the 8th minus 5x plus 8, all these terms are separated by addition and subtraction, so that's fine. And it is simplified all the way. You can't do any combining. But you actually do need to put this in decreasing order. All the degrees need to be, or exponents need to be in decreasing order. So we're going to start with 6x to the 8th, and then we're going to go with 7x squared minus 5x plus 8. Remember that x always has a hidden exponent of 1. The one below it does have all the exponents in decreasing order, but we do have some terms we can combine. So this 3x to the second and this minus 4x squared, those are like terms. So I'm going to combine those. So I have 6x to the 8th minus 7x squared minus 5x plus 8. So then once your polynomial is in standard form, there's a couple things it tells us. It tells us, one, the number of terms. Okay, so we can combine any terms that repeat. The second thing it tells us is the degree of the polynomial, and finally that leading term or leading coefficient. Okay, and what these things help us do is eventually we're going to learn how to graph them. So if we can identify what these three things are, leading term, degree, leading coefficient, eventually we're going to be able to describe the end behavior, which will help us graph each one of these polynomials. So identifying the leading term is pretty easy if it's in standard form. It's just the term in front. So for this first one here, I think my leading term is 4x. So my leading term is 4x. Remember, it's always hidden exponent of 1. The degree is going to be 1, so it's a first degree or 1 degree term. The leading coefficient is going to be that coefficient, the number multiplying by your variable. So it's going to be 4. For this second one, your leading term is negative 3x to the second, which means my degree is 2, my leading coefficient is negative 3. And then finally for this bottom one here, I think my leading term is 2x to the 4th, which means my degree is 4, that exponent of 4. And then finally, my coefficient, my leading coefficient is 2. So finding that leading term really is the key, because once you know what the leading term is, you should be able to figure out what that leading coefficient and degree are. So in these three practice problems here, if we're going to identify each leading term, I'm going to start with 3x to the third plus x to the first. As long as it's in standard form, which it is, that leading term is just the one in front. So my leading term in this case is 3x to the third. The next one's a little trickier because it's not in standard form. So remember, in standard form, you've got to have that polynomial written so those exponents are decreasing. So I'm going to rewrite this as negative 2x to the 5th minus 2x squared plus 7. So then I can easily see, we can kind of show that my leading term then is negative 2x to the 5th once it's in standard form. Finally, this last one, which is kind of tricky, that is not in standard form because it's not simplified and it's also not in decreasing order. So I'm going to combine the 9x to the third plus 3x to the third. I'm going to make that into 12x to the third. But then I'm going to make sure I rewrite it. So it's 12x to the third plus 5, which means my leading term is that 12x to the third. So why is this important? Why is it important to determine, what the leading term and the leading coefficient, the degree, why does it help us? If you look at a pattern of graphs, you'll notice that the degree, the leading coefficient, they can kind of dictate or tell you what the end behavior of the graph is. So you'll notice in group 1 how each of these polynomials, all of them have an even degree, okay? So they got a 4th degree, and then a 6th degree. So all these degrees are even, okay? And they also have a positive, so even degree, and a positive leading coefficient. And if I were to describe the end behavior of group 1, okay, I would describe it kind of as up left, up and to the left, and up and to the right. And I kind of abbreviate this as I'm doing these problems. I do UL, UR. You can do either one, okay? Let's look at group 2. So I want you to notice once again that in group 2, those degrees are positive. So because my degree is positive, 4, 4, 6, for each of these in group 2, okay, so we got a positive degree. You'll notice that the end behavior is going in the same direction, but this time it's not going up. No, this time it's not up, left, up, right. This time it's down. And the reason why it's going down is because of that, coefficient, that leading coefficient, which in this case, happens to be negative, okay? So this pattern that I want you to notice is that really, if you know the even or oddness of the degree, and if you know the sign, positive or negative, the leading coefficient, you should be able to tell me what the end behavior is of a graph. Let's take a look at 2 other situations. So here in these, really 6 graphs, every single degree is odd. And I want you to notice how, even in the ones that are positive versus negative, because my degree is odd, the end behavior is not ending in the same direction, okay? When the degree is odd, okay, so if I have an odd degree, I also have, a positive leading coefficient. My end behavior, it's opposite, right? It's kind of it's not both going in the same direction. It's down left and then up right, okay? And that changes a little bit when we get to, an odd degree, but the leading coefficient is now negative, okay? Because now it's up left, up and to the left, and down and to the right. So to summarize these situations, if you have an even versus an odd degree, your end behavior is going to change. And if you have a positive versus a negative leading coefficient, your end behavior is going to change as such. So this chart here just kind of helps you summarize, even versus odd degree. Okay, so if we have an even degree, a positive leading coefficient, my graph's going to look something like that, okay, which is going to make it, which would mean my end behavior then is up left and up right. For an even degree with a negative leading coefficient, the graph kind of looks like an upside down parabola, down left, down right, and I'm using these abbreviations DL, DR. For an odd degree with a positive leading coefficient, so top right box, kind of looks like that cubic, right? Or you could think of it as like a linear equation. So it's down left, up right, or a negative leading coefficient in an odd degree. So that bottom right corner box kind of be almost like an upside down cubic, right? Or you can think of a line with a negative slope. So it's kind of that up left, down right. So if we're going to describe the end behavior, and the equation's written in standard form, really the only thing we're looking at is that leading term. So for this first one, my leading term has a negative leading coefficient, and it also has an odd degree. Therefore, this is going to be an up left, down right polynomial end behavior. For this next one, the leading term 4x to the 4th. That is going to be a positive even degree, positive leading coefficient, even degree. So it's going to go in the same direction. So it's going to go up left, up right. Okay. For this last piece here, it's got a leading coefficient of 3x to the 7th power. So that's a positive leading coefficient. And an odd degree, so that's 7, right? So this is going to end up being a down left, up right graph. So next we're going to take a look at end behavior when it comes to, factored form, okay? So remember, all these rules we've been building in only relate to standard form. So one of the strategies some students use is they, multiply, or they, distribute, or they FOIL, polynomials out, so then they put them in standard form, and then they can find out what the end behavior is. We're going to learn today that that's not necessarily what you have to do. You could do that, but there's kind of an easier route. So if we wanted to find, the leading term from factored form, we could FOIL. So let's take a look at this first example. We could FOIL this. We can multiply 2x to the third by 4x to the third and get 8x to the sixth. Okay, and then multiply the outside, inside, last terms, and we get this really long standard form polynomial. What I'm telling you is we don't actually need to FOIL completely. The only thing we're really looking at is the first terms, 2x to the third and 4x to the third, because those are going to give us our highest degree term in our polynomial. So in these practice problems, it says find the leading term and describe the end behavior. Okay, so once again, I could FOIL this whole thing. I could go first, inner, outer, last. I could get this really long polynomial, okay? But there's an easier route. We really just need to multiply the first times the first. So x to the eighth times 2x. Numbers by numbers, so 1 times 2 is 2. And then x to the eighth times x to the first. X to the eighth times x to the first is x to the 8 plus 1, or x to the ninth. Okay, so my answer is going to be 2x to the ninth, which means this is a positive, odd polynomial. So my end behavior is going to be down, left, upright. For this next one, it looks a little more confusing because now there's some coefficients in front of my first terms and each binomial, but it's really the same thing. I really just have to multiply 3x to the third times negative 5x. So 3x to the third times negative 5x, numbers by numbers, negative 5 times 3 is negative 15. Variables by variables. X to the third times x to the first is x to the 3 plus 1. So the final answer is going to be negative 15x to the fourth, which is a negative even. So that means that my polynomial is going to be down, left, down, right. So let's think just conceptually what this means, okay? Because if I'm writing down this end behavior, these directions, down to the left, up and to the right, or down to the left, down to the right, what does that mean? It means that, I could actually graph on my graph down, left, down, right. Now, I don't know what the rest of this polynomial is going to look like. I don't know what all this stuff up here does, but it's kind of like the beginning to a puzzle. You don't start in the middle of a puzzle and work your way out. You start with the corners. So right now we're starting with the end behavior to the left and end behavior to the right. Kind of the same logic applies if we're trying to find the end behavior if there's more than 2 factors, okay? Do we need to FOIL everything out? Do we need to multiply x plus 1 times x minus 3 times x plus 4? No. We really just need to take a peek at the first terms in each individual parentheses or each individual binomial. So really, in order to find the leading term, okay, all we need to do is multiply x times x times x, which is x to the third. So in this first example, okay, it says describe the end behavior of the following polynomial. I really just need to multiply x times 2x times x, and that's going to give us my largest degreed term. So x times 2x times x, numbers by numbers, 1 times 2 times 1 is 2. Variables by variables, x times x times x is x to the third. For this next one, things get a little trickier, but it's still doable, right? Because we don't have to multiply everything out. All we have to do is multiply these first terms. 2x to the third times 3x times negative x, and that's going to give us our leading term. Okay, so this would be 2x to the third times 3x times negative x. Okay, so numbers by numbers, so 2 times 3 times negative 1 is a negative 6. Variables by variables, x to the third times x to the first times x to the first is x to the fifth. So this is a negative, odd polynomial, which means it's going to end behavior is going to be up and to the left and down and to the right. So on that graph, we know that over here to the left, I'm going to have an arrow pointing up to the left. And over here to the right, I'm going to have a variable pointing down to the right. We don't know everything in the middle yet, and that's okay. We're going to learn it later this week. But for now, we know what the end behavior is. And the last piece for this today is going to be, a really complicated looking polynomial that's raising binomials to the power of 2 or 3 or 4, okay? So I want you to think about this because x to the fourth plus 1 squared, that's really x to the fourth plus 1 times x to the fourth plus 1. And x minus 3 to the third is really x minus 3 times x minus 3 times x minus 3. And x plus 4 is just a normal x plus 4, okay? So with that thought in mind from the previous problem, I could combine these. So x to the fourth, x, 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 and x. So if I want to know that leading term, I really just got to multiply these together. So x to the fourth times x to the fourth times x times x times x times x, which would give me x to the 4 plus 4 plus 1 plus 1 plus 1 plus 1, or x to the 12th. So what if I don't want to expand this? Because that was kind of a lot of work, okay? Is there a shortcut? Well, yeah, just like we didn't really have to worry about foiling the whole thing out, you really don't have to expand the whole thing out. You just need to know that, a power to a power is really multiplication of powers. So I'm going to rewrite the problem from above, and I'm going to do it again, but this time I'm going to raise x to the 4th to the 2nd power. X to the 4th to the 2nd power. Instead of expanding it, I'm going to raise x to the 3rd power instead of expanding it. Notice how I'm putting these, groupings in parentheses. X to the 4th to the 2nd power, x to the 3rd power. And then finally, x, to the 1st power is just x. And then I'm going to simplify. X to the 4 raised to the 2nd power is really x to the 8th. And x to the 1st raised to the 3rd power is really x to the 3rd. And then x to the 1st power raised to the 1st power is still just x to the 1st. So this becomes x to the 8 plus 3 plus 1, which is x to the 12th. See how we got the same answer? But I would say the bottom way is a little quicker if you don't expand everything. You just remember that power to a power. So for these last two, I'm going to emphasize something on that next one, but this one is kind of just more practice, okay? So if I want to find the, end behavior of this following polynomial, I really just need to find that leading term. So x to the 3rd, x to the 4th raised to the 2nd power, x and x. I've got to multiply those together. So x being raised to the 3rd power, x to the 4th, make sure you put it in parentheses, being raised to the 2nd power, x and x. Okay, and then I'm going to simplify. So x to the 3rd, x being raised to the 3rd power is just x to the 3rd. X to the 4th being raised to the 2nd power is really x to the 8th. And then x and x are just x and x. So this becomes x to the 3rd times x to the 8th times x to the 1st times x to the 1st, which, if we're multiplying variables with the same base, you can add the exponents. This becomes x to the 3 plus 8 plus 1 plus 1. Or x to the 13th, which is a positive leading coefficient and an odd degree, meaning this graph is going to be a down left upright, okay, using that chart. So, conceptually, what does that mean? It means that, it's going to be down and to the left, but it's also going to be up and to the right, and everything in the middle is going to, we don't know yet, but we'll get there. For this last one, now we have some coefficients in front of the variables we're raising to a power, okay, but still the same principles apply, okay? So we got a negative in front, so that's going to stay in front. Next, I've got a 2x squared being raised to the 2nd power, so I'm just looking at these, first terms of each of these binomials. Then I've got a 3x squared, and that's not being raised to a power, so 3x squared. And then I've got an x to the 4th, and that's also not being raised to a power, okay? So if I want to raise, the negative is going to stay negative in front. If I want to raise 2x squared to the 2nd power, really this becomes 2 squared times x squared raised to the 2nd power, okay? So, rewriting that, I would really have, of course, negative 4x to the 4th, okay? That is a raising to the power of 2. That's not multiplication, it's raising to the power of 2, okay? And then I'm left over with 3x squared and x to the 4th. So now it's just business as usual. So numbers by numbers, negative 4 times 3 is negative 12. Variables by variables, so x to the 4th plus 2 plus 4. I think that's going to end up giving me a positive 10. So this would be negative 12x to the 10th, which means I've got a negative, even, so I've got a down left, down right polynomial.